current model is as follows. We have a diatomic, and we use 7 low-energy vibrational states, 0 to 6. And within each of those vibrational states, we have 9 low-energy rotational states, for a total of 63 low vibrational states. From those states, we choose 4 to represent our qubits in this kind of cyclic nature here. We shape in the mid-infrared with amplitude and phase variation accordingly, and we use the genetic algorithm in order to determine our optimal pulse shapes. So inevitably, we're shaping laser pulses to represent quantum logic gates. And this is just to show the structure in the frequency domain. So what are the relevant questions that I thought were necessary to answer? Typical calculations in this area: simply choose a molecule and shape a laser pulse and see how well it does. What's more interesting to us is whether the choice of diatomic matters. So does it matter if I pick CO, or does it matter if I pick a different molecule in terms of being able to shape laser pulses? Secondly, is related to the laser pulse shaping. So there are a set of parameters I've shown there. What are those parameters, and which ones are relevant for the shaping and getting high fidelities? So is changing the resolution important? Is changing the number of frequencies important? And obviously, is amplitude and phase important? And how much do we need to vary those accordingly? So I'm going to go through each one of these and just show you some results to illustrate which ones are and are not important. A diatomic can be modeled, as I showed you probably in the 4th slide, as an oscillating, rotating molecule. And if you want to represent the energies as a Taylor series expansion and vibrational rotation, you obtain this long equation. The terms that are relevant for us are the anharmonicity term and the rotational constant term. And Irakura in 2000 collected all this information and published a paper that had the experimental data for these 2 parameters for a bunch of diatomics. And that's what I plotted here. So what's plotted here is the anharmonicity versus rotational constants for a set of diatomics shown in blue. I've neglected the diatomics containing hydrogen and deuterium. They exist in a different part of the curve. This is quite linear, so I drew a best fit linear curve, and then I sampled along this linear curve, inevitably varying the choice of diatomic. Okay, and I did this for the ACNOT 1 gate with 51 frequency components and 2 amplitude and 2 phase variation of 0 or 1 and 0 and pi. And this is the result. So on the x-axis is the anharmonicity, or rotational constant, depending on how you want to look at it, and the resulting fidelities. And there is obviously an inherent structure that is diatomic dependent. So at times, if you choose, say, this diatomic, you get near 100% fidelity, whereas at times you can get near 40% fidelity. So there's large fluctuations depending on which diatomic you choose. The frequency waveform was varied and is synonymous with the total pulse duration. So throughout this talk, I'm going to talk about total pulse duration, but it's synonymous with frequency width. And I did this for the ACNOT 1 gate. I chose a specific diatomic, and that was CO. I simplified the setup, and I just chose the central frequency, so 1 frequency component with an amplitude of 0 or 1 and 0 and pi. And this results in 4 different fields that I can generate, and those are shown in black, red, and blue. So in black is the case when the amplitude is 1 and the phase is pi. Red is the case when the amplitude is 1 and the phase is 0. And blue is the case when there is no amplitude, i.e. there's no field. So there is, again, some structure here. It seems somewhat repetitious. I didn't extend it beyond, say, 60, 70 there. So it could repeat itself. But inevitably, the frequency width fidelity does depend on the frequency width. Moreover, for the case when the field is on, it seems to represent or follow the same curve. It's hard to see in this diagram, but in blue here. So when the field is off. So what does this no field A is equal to 0 represent? It doesn't mean that the fidelity is 0. Keep in mind the fidelity represents all possible qubit representations. So what it does mean is that this transition no longer occurs, there's no field, but these operations can still occur. And so what's actually happening here is this is showing the alignment of qubits 1, 0, and 1, 1. So when the fidelity is 0, we have no alignment. When the fidelity is about 25%, they're realigned again, and this occurs oscillating over time, depending on how long the pulse is. To show the effective amplitude, I switched and used the NOT 2 quantum logic gate, shown here. Same molecule, CO. In this case, I have to use two frequency components, so here and here. And I just chose a set of 5 different total posturations, or frequency widths, however you want to look at it. And when I optimized these laser pulses, I obtained low fidelities when the amplitude was 2 and then the phase variation was 2. When I increased the amplitude to 512, fidelities increased dramatically, and in some instances over 99% fidelity. So in this case here, when the total posturation is 44 picoseconds long approximately, I get almost 100% representation of quantum logic gate operation by this laser pulse. So amplitude is important. And the next 2 examples of number of frequency components and phase variation, I'm going to use the example in the bottom here. So 0.8459 fidelity, as shown here. So same setup, not 2 gate operation and CO. I varied the number of frequency components from 2, so 2 initial frequency components are shown in bright red, up to 10. And in order to get 10 frequency components, I just added more frequencies on either side of these central frequencies here. So going from n is equal to 2 to 10, the fidelity changes a little bit, 5% or so. So the number of frequencies is subtly important. I think the most important thing to take home from this is that the majority of the fidelity is a result of these 2 frequency components. And the addition of more frequency components just incrementally adds to the fidelity. Lastly is the effect of phase variation. Same table, looking at 10 frequency components. I increased the phase from 2 to 32 frequency components, or phase components, sorry. And the resultant fidelity does not change much at all. So phase doesn't seem to be a very important factor for producing high fidelity laser pulses to represent quantum logic gates. So for the entirety of the talk, I've been talking about 2 qubit operations. So you may be wondering, how many qubits are necessary in order to actually perform something on a quantum computer, something interesting? In fact, you need about hundreds and thousands and millions, so you need quite a lot. And so scalability is always a problem when building up a quantum computer. Scalability meaning the addition of more qubits. And in my case, it is a big problem. Because the number of rovibrational states I need to use to represent my qubit scales as 2 to the power of q, q being the number of qubits. So when I had 2 qubits, I had 2 to the power of 2, 4 rovibrational states. If I want 100 qubits, I need 2 to the power of 100 rovibrational states. So not very feasible. So where is this applicable? So DeMille proposed a quantum computer using polar diatomics and an optical lattice. So we have a chain of polar diatomics along here and an electric field gradient. Okay? And each of these diatomics now represents a specific qubit because we have a 2-level system here. Okay? This 2-level system could be expanded. I'm going to be specific here. It's a 2-level rotational state representation. But these 2 levels could be extended to 4 states, as in my example, using the rovibrational states instead. And so scalability is not so much an issue here because all you have to do is then add more and more diatomics in order to increase the number of qubits. And since they're polar, there's dipole-dipole coupling, so you can get 2 qubit operations. So this is a very feasible method for a quantum computer. So to conclude, hopefully I've at least conveyed the importance of a quantum computer, if we ever get one. I've shown the example of what I do with the diatomic quantum computer, where the qubits are represented by rovibrational states, and quantum logic gates are implemented via laser pulse shaping. Moreover, I showed that the choice of diatomic is important, and in relation to the laser pulse shaping parameters, the frequency width, the number of frequency components, and the amplitude are also important, and the phase, not so much. In the end, I showed that my current implementation may not be as practical as is, but applied with DeMille's method could be used and perhaps furthering the field of quantum computing. So I'd just like to thank everyone from the Brown Group from over the years. There's some people in the audience here. And obviously my peers down